For over a century, physics has carried within it a strange and unsettling idea that reality does not behave the same way when it is observed. At first, it sounded like philosophy disguised as science, something too abstract to be real. But the deeper scientists looked into the quantum world, the more undeniable it became. At the smallest scales of existence, particles do not move along fixed paths like planets around a star. Instead, they exist in probabilities scattered across many possible outcomes at once, as if reality itself hesitates before choosing what it will become. And then comes the moment of observation. The instant a measurement is made, that haze of possibility collapses into a single outcome, a single reality. This is the observer effect, first formalized during the early quantum revolution by physicists like Werner Heisenberg, whose uncertainty principle revealed that even the act of knowing introduces limits to what can be known. Not because of human error, but because nature itself behaves differently when it is measured. For decades, this idea remained one of the most uncomfortable truths in science. It suggested that observation is not passive. It is participatory. Yet it was still widely assumed that this collapse was unavoidable, a kind of fundamental noise in the structure of reality. But in a modern quantum research environment, something unexpected began to challenge that assumption. Deep inside superconducting chambers operating at temperatures colder than interstellar space, researchers working with advanced quantum processors began experimenting with a different kind of measurement. One that did not simply look at quantum systems, but continuously interacted with them in real time. The work developed in advanced facilities associated with quantum computing research programs used superconducting circuits designed to hold quantum bits in delicate coherence long enough to study their evolution step by step. Instead of allowing a quantum state to collapse instantly upon observation, the system attempted something more subtle. Sustained predictive tracking, where measurement and computation became a single intertwined process. At first, the results appeared to confirm standard quantum behavior. Particles still fluctuated between states, still followed probabilistic distributions, still resisted classical prediction. But as the systems became more refined, researchers introduced continuous feedback loops powered by real-time computation. These loops did not merely record outcomes. They adjusted the measurement process itself, anticipating changes before they fully manifested. In a sense, the experiment stopped being a snapshot of reality and became a moving conversation with it. And within that conversation, something unusual began to appear. Under persistent observation, certain quantum states did not collapse as expected. Instead, they stabilized. They became unusually coherent, maintaining structure longer than predicted by conventional models. It was as if the system was learning how to remain consistent under attention, as though observation itself was becoming part of its internal dynamics. This behavior led researchers to describe a tentative and controversial concept sometimes referred to as self-stabilizing coherence. In this regime, quantum systems appeared less like fragile probabilities and more like adaptive structures responding to measurement pressure. The longer they were observed, the more predictable they became. Not by losing their quantum nature, but by reorganizing it. The effect was subtle, yet persistent enough to survive repeated experimental variations. Each time, the same pattern emerged. Observation no longer simply forced a collapse. It influenced the trajectory of collapse itself. The boundary between measuring and shaping began to blur. As the experiments evolved, an additional layer was introduced. Machine intelligence. A quantum-trained neural system analyzed incoming data streams in real time, not after measurement, but during the measurement process itself. This system did not interpret reality in human terms. It detected patterns in probability fluctuations, correlations hidden inside noise, and structure within what previously appeared random. Over time, it began adjusting measurement strategies in ways no human-designed algorithm had explicitly programmed. It learned which forms of observation preserved coherence and which disrupted it, effectively becoming a participant in the experiment rather than an external tool. The system's behavior suggested a new kind of loop. Quantum state influencing computation, computation influencing measurement, and measurement reshaping quantum state. What emerged from this tri-layer interaction was not a violation of quantum mechanics, but something far more subtle and unsettling. Reality at this scale appeared responsive. Not in a conscious sense, but in a structural one. It reacted to sustained interaction as if a tension properly defined through physical coupling and feedback altered the stability of what was being observed. Some theorists cautiously proposed that this might point toward deeper frameworks beyond standard interpretations of quantum mechanics. Frameworks where observation is not an external act, but an embedded physical process within the system itself. Others suggested that this could represent an early glimpse into regimes relevant to quantum gravity, where spacetime, information, and measurement are not separate concepts, but different expressions of the same underlying